Welcome back. So we were talking about maintaining privacy of individuals while still learning something useful about the population. And we talked about this simple example of randomized response where people participating in the survey were utilizing noise, perturb their truth to maintain privacy while still providing useful information for our learning problem. Now, it is also very intuitive to think about the privacy of a certain learning model through the lens of sensitivity. Okay? So to see this, consider the following example. Again, let's go back to our example of randomized response, learning which fraction of professors are playing video games. And now assume that a professor retires, okay? And the department hires a new assistant professor, okay? Now, what will happen to our survey? Okay. Again, let's consider those two extreme cases. Case one, everyone is being truthful. Case two, everyone is lying. Okay. So in case one, our survey is actually highly sensitive to this change. Okay. Essentially, if someone gains access to the outcome of two surveys, one with the retired professor answer, the other one when we instead have the answer from the new assistant professor, we can essentially learn something very specific. Okay, by looking at the difference between these two surveys, we can learn something very specific about the new hire as well as the retired professor. That's why we basically say that under this case one, our survey is highly sensitive to this change. Okay. On the other hand, if you consider the second case where everyone is sort of lying or providing random response, completely random response, which is useless, then our survey is completely insensitive. It doesn't matter if I'm looking at the survey with the retired professor or with the new hire. They would both sort of provide a random response. So on average, the survey is basically the same. So it's completely insensitive to this change. Okay. And the idea is that, again, noise tends to reduce the sensitivity of our method. And in this case, it is improving the privacy of our learning model. Okay. And this idea of sensitivity gives rise to what we refer to as the differential privacy. Okay. Essentially, we want to have methods that are not too sensitive to individuals in let's say, or individual data points in our training data. Meaning that if I change one data point to something else, the outcome of my learning algorithm does not change much. Okay, so essentially, let's look at these plots. Let's say that this is the outcome of the learning algorithm. In this case, the survey with the retired professor. Okay, under case one. So this is the basically under case one. Under case one, there is a huge change in the distribution of the outcome. Okay, because of the sensitivity. On the other hand, under case two, or something that interpolates case one and case two, so let's call it randomized response then. Under randomized response, when I replace this retired professor with a new hire, the distribution of the outcome does not change much. So therefore, the outcome is not as sensitive to this change. So what we want to therefore ensure that happens, or essentially what we want our learning algorithms to satisfy in order to maintain the privacy of the individuals is as follows. In this example, we want to make sure that the probability that the outcome of the survey is in some outcome set. When I look at the entire department with the retired professor, is exactly or roughly the same as the probability that the outcome, again, belongs to the same outcome set. When I look at the survey, including the department, but instead of the retired professor, I'm looking at this new hire. Okay. Now, what we're going to do in the next slide is to sort of formalize this approximation, okay, and therefore drive the definition of differential privacy, okay. To do that, we have to first define neighboring data sets, okay, and this is essentially like what we talked about before, having the department. One case you have the retired professors, and in another case you replace the retired professor with a new assistant professor, okay. So two data sets, let's say D and D prime, are said to be neighbor if they differ in exactly one sample, okay? And we typically use this notation to denote that D and D prime are neighbors, okay? Given this definition, we can define differential privacy. In particular, the definition is going to have two parameters, epsilon and delta, which to some extent characterize the degree that the privacy is maintained, okay? So epsilon delta differential privacy, or epsilon delta DP, is given by the following definition. Let's assume that you have a collection of data sets and a randomized mechanism or randomized learning algorithm, M. M is said to be epsilon delta differentially private if for any two neighboring data sets, meaning that two data sets that they differ in exactly one data point, and for all sets of outcome, okay, so this could be like the outcome of the survey we were talking about in our running example, the following condition is satisfied. The probability that the outcome of my learning algorithm belongs to set R when I use data set D, let's say as a training data, is bounded by e to epsilon, okay, this is the exponential function, times the probability that the outcome of my learning algorithm belongs to the same set R when I use D prime as the training data, plus some delta, some parameter delta. But epsilon and delta, as I mentioned, are the privacy parameters that are non-negative, okay? So why, again, this is exactly talking about the notion of sensitivity, okay? For instance, let's say delta is equal to 0 and epsilon is also equal to 0, okay? So when epsilon is equal to 0, epsilon, e to the epsilon will be 1. So what this is saying is that when I change one data point to go from D to D prime, the probability that my outcome belongs to set R does not change much, meaning that my learning algorithm is basically insensitive or approximately insensitive with respect to this change I'm making in my training data. Okay, so therefore I think the most intuitive way to think about this definition of differential privacy is through the lens of sensitivity. Okay, so algorithms are differentially private when they are not sensitive with respect to changes in the training data. Okay. All right. So let's talk about some remarks and some terminology. So when delta is equal to 0, this definition is sort of known as pure differential privacy or pure DP. Otherwise, sometimes we refer to it as approximate differential privacy. Okay. Now, when you first look at this definition, the appearance of e to epsilon seems very peculiar. Okay. And the idea is that e to the epsilon is actually mostly, I would say, for mathematical convenience. Okay. And you could have used, let's say, 1 plus epsilon here to sort of characterize how much the probability will change, okay, when I change one data point, okay? So we could have used 1 plus epsilon, and indeed, these two are roughly the same, for instance, using Taylor approximation, when epsilon is very small, okay? Another peculiar thing about this definition is that at first glance, it seems asymmetric. Okay, so we have D on one side and D prime on the other side. But in fact, this is a symmetric definition because it says that this inequality should hold for all or for any two neighboring data sets. So I can easily just switch the role of D and D prime and then get another sort of inequality. So therefore, what it's saying is that when I change one data point, it doesn't matter if I go from D to D prime or D prime to D. When I change one data point, my algorithm is not going to be too too sensitive, meaning that the outcome is not going to change much. All right. And there's also a very simple exercise that you can do to convince yourself that this definition can only be satisfied by randomized mechanisms, randomized learning algorithms. If your mechanism is deterministic, there is no way to satisfy this condition. This again highlights the importance of leveraging noise perturbation, randomized perturbation, to ensure privacy. Okay, and in some sense, therefore, you may expect that the algorithms we use to train deep learning models could satisfy privacy in some sense, because, for instance, we are using randomized mechanisms, right? When optimizing deep learning models, we are using SGD, which is a randomized algorithm. We are using batch normalization. We are using dropout, etc. All of those are randomized mechanisms. They are injecting some noise in some sense, and that noise could actually contribute in improving the privacy-preserving property of our deep learning models. Okay. So let's also talk about another terminology. So I'm not going to talk about the derivation of this, but I think this also provides a very intuitive way to talk about the definition of differential privacy. Okay. So this ratio. So let's look at this log ratio. The log of a ratio of, again, the probability when I use D as my training data over the probability that I use D prime as my training data. This is actually sometimes is referred to as the loss of privacy, or the privacy loss. Okay, and if you have a differentially private algorithm, which is, let's say, epsilon delta dp, the way that you can interpret the result is to say that for this specific algorithm, the privacy loss is less than epsilon with high probability, with probability that is at least 1 minus delta. Okay, so therefore epsilon, you can think of it as the extent of privacy loss, and delta, you can think of it as some notion of confidence. Okay, such that again, epsilon delta dp means that the privacy loss is at most epsilon with high probability, with probability at least 1 minus delta. Okay, so therefore epsilon and delta are basically our privacy parameters, and the smaller they are, the stronger the privacy guarantee. Okay, so again, in the limit when epsilon is 0 and delta is 0, what we are saying is that with probability 1, the loss of privacy is 0. Okay, so the best case. So therefore, they control the privacy accuracy trade-off. Okay, as we saw in the randomized response example, the more randomization we are injecting, or the more noise we are injecting, the higher the level of privacy, but the worse the accuracy will get. Okay, so there is therefore inherently a trade-off between privacy and performance, and we can control them, or we can characterize them in this case by parameters epsilon and delta. Okay. Now in practice, typically epsilon is said to be something that is less than 0.1. Okay, and delta is actually said to be something that is very smaller or significantly smaller than 1 over n, where n is the number of data points. So what this is doing is ensuring that the privacy loss for each data point is small with high probability. Okay, so therefore again, it's a very simple example. You can use something like a union bound to show that to ensure the privacy loss for each specific data point is small, we have to set delta, this global notion of privacy, if you will, to be significantly smaller than 1 over n. Okay. All right. So there are a lot of important and elegant results when it comes to differential privacy, and here I'm going to highlight one of these to basically say that differential privacy is actually a very meaningful and useful definition. In particular, if you have a differentially private mechanism or a learning algorithm, regardless of what others do with the outcome you'll be releasing, the outcome will still be differentially private. So this is going to result in this simple theorem that is referred to as the post-processing theorem. Okay, again, let's say you have a mechanism or a learning algorithm which is epsilon delta differentially private. Then if you compose it with any other function h or h, the outcome will again be epsilon delta differentially private. So therefore, no matter what others do to the release outcome, privacy is maintained, as long as the original learning algorithm was epsilon delta differentially private. Okay? So therefore, it is natural to ask a question whether our randomized response example is actually a differentially private mechanism. And thanks to this post-processing theorem, we can actually prove that randomized response is differentially private. Okay, so let's go back to our examples on professors and video game again then, and let's consider two neighboring data sets. So D and D prime. They're all the same except that I change x1, which again could be the retired professor, to x1 prime, the new assistant professor that is hired. Now, everyone is again incorporating randomized response, noise in the response they provide to the person who is conducting the survey. Okay, and if you recall, to get a good estimator of the fraction, the person conducting the survey would do some rearrangement of the responses and then form an unbiased estimator of x bar, and then would use that. Okay. So we can think of that process as this function h that we had in the post-processing theorem. Okay, so everyone is providing some response. If those responses are basically differentially private, regardless of what the person conducting the survey, the estimator of the fraction should also be differentially private. Okay. So therefore, by post-processing theorem, all we need to do is to show that this randomized process, randomized response process, is differentially private. We don't care about the rearrangement that is done by the person conducting the survey. Okay. So what is our process? Therefore, our process is exactly the randomized response. Everyone would provide some response y I, which was exactly equal to xi with probability half plus epsilon, and 1 minus xi, sorry for the typo, with probability half minus epsilon. So they would be truthful with probability epsilon plus half, and they would sort of lie with probability half minus epsilon. So on average, they tell the truth more than not. Okay. So let's look at therefore our mechanism. So MD is basically the collection of all of the responses that the professors are providing. Okay, where I'm going to call yi to be basically the output of the mechanism that the IS professor is using. Okay, and again, this mechanism, as you can see, is a randomized mechanism. It takes the original truth xi, and then it injects some noise to it. Okay, in this case, a binary noise. And then the outcome will be yi. And that's something that is given to the person conducting the survey. Okay, so let's consider a potential outcome. Okay, R, which is essentially a vector of size n, where the entries are only 0 or 1. Okay, so the IS entry indicates the response provided by the IS professor. If that entry is 0, it means that the professor is telling that they are not playing video game, and if an entry is 1, this says that that professor is basically saying that they are playing video game. Okay, so let R therefore be a possible response profile, and we are going to assume that the responses are statistically independent. Okay, so to show differential privacy, we have to look at this ratio basically. Okay, again, the log of this ratio was referred to as the loss of privacy. So if this ratio is bounded, the loss of privacy is bounded, therefore the mechanism is differentially private. So let's look at this ratio and note that we are assuming that the responses are statistically independent. These two data sets are the same except in one position. Okay. So using this, I can write this joint probability as the product of the marginals and do the same for the denominator. Okay. And note that these are again, so the terms here, so this actually also appears in the numerator because again, these data sets are the same, they're neighbor, so they are the same except in one position. So it means that I can get rid of the common factor in the numerator and denominator. So all I'm going to be left with, therefore, is basically the probability that the response of x1 is R over the probability that the response of x1 prime is R. Okay. Now, this is actually something that we can bond using our randomized response process. Okay. So again, randomized response is that they provide some answer with probability half plus epsilon and another answer with probability half minus epsilon. So I can bond this ratio by using the larger probability for the numerator and the smaller probability for the denominator. Okay, so that means that I'm going to use half plus epsilon to upper bound the numerator and half minus epsilon to lower bound the denominator. So therefore, I'll be able to get an upper bound on my ratio. Well, so the last step is to actually write this down in terms of e to, let's say, some constant times epsilon. And again, using some basic formula, we can actually do this. Okay. So it turns out that for any epsilon less than 0.3, therefore, randomized response is 5 epsilon and 0 differentially private. So that means that the loss of privacy is at most 5 epsilon, as long as epsilon is less than 0.3. Okay. All right. So there you go. So therefore, we talk about randomized response. We talk about differential privacy as a formal way of talking about the privacy preserving property of learning algorithm. And as I mentioned, in my view, the most intuitive way to think about that definition is to think of it as capturing how sensitive a learning algorithm is with respect to changes happening in the training data. Okay, and we also just showed that randomized response is an example of a differentially private mechanism. Okay, so in some sense, randomized response is a scenario where our outcomes are binary, so they are a single bit, either 0 or 1. Okay, but we want to see how we can leverage this idea in general cases where our responses are not necessarily binary. For instance, if I'm releasing the weights of a deep learning model, that is, I can think of it as a very long vector. Each coordinate is a real variable. Okay, how can I make sure that after releasing the weights, I'm not losing privacy? In other words, how can I leverage noise to make sure that my mechanism or my learning algorithm satisfies differential privacy? And this is something we're going to talk about in the next video. I'll see you there.